We are live now. Please start.
Okay. Hello and welcome to this interactive session on machine learning course of NPTEL. So we saw that some of you were facing problems in solving numerical questions in the assignments. So we thought of conducting this session to handle some of your queries. So we shared a form with you, but we did not get many questions over there. Anyway, so what we are going to do in this session is I'm going to take a few questions from the assignments and the numerical questions, and I'll be discussing the solutions to these questions. Meanwhile, if you have any questions regarding what we are discussing or in general any other question which we are not discussing, you can write in the chat box and I'll be taking a look at the questions in your chat at the end. Yeah, so I'm going to share a slide and let's take a look at that. Okay, so so this is one of the questions. So I'm going to take different questions in sequence. You keep writing your queries in the chat box. So the first question that we're going to take is of a single neuron. So as we know, the concept of a neuron is such that it takes a few inputs and then there are weights. Every input has a different weight. And then based on these weights, we compute a function, and then that is what is output, right? And then whether that output matches with what we desire or not, we keep changing the weights. So that's the simplest idea of a neuron. So in this question, there is a single neuron and there are three inputs, x1, x2, and x3, and there are three weights, w1, w2, and w3. And we have to find the weighted sum of these inputs. And also, once we get the weighted input, we apply an activation function. So there are different activation functions that are used in neurons. So here in this question, we have to use a sigmoid function that is shown here. And the formula is also given 1 over 1 plus e to the minus x. So if x is input to it returns, it gives as output 1 over 1 plus e to the minus x value. So that is what is the output. So these values are given to us, and what we are supposed to find is the value of y. So what we are going to do here is we are just first computing the weighted sum. So x1 into w1 plus x2 into w2 plus x3 into w3, that's the weighted sum. And apart from that, we also have a bias b, which is also given to us to be minus 6. So we are simply computing here the weighted sum, and bias is also added. So we get 1 over here, right? So that's the weighted input, and that we will get over here, and that will be fed to the function f, which is the sigmoid function over here. So 1 will be fed to the sigmoid function. So when we input 1, we get 1 over 1 plus e to the minus 1, and that comes out to be 0.73, right? So that's the simplest I think that's the simplest question in a neural network chapter, right? So that's the basic one, because we have one single neuron. Because in practice, what we have is we have different layers of neurons. We have input layer, and then we have output layer, and in between we have a number of hidden layers. So that's the whole network. So here what we're talking about is a single neuron. That's one node in that network, right? So that it's very simple. We are given the inputs, we are given the weights, and then we compute the weighted input, and we apply the activation function, and that's the output. And then we compare the output with what we intend to get, and based on the difference, we keep on changing the weights, which we will just discuss. So that's not what is required here. We just want to compute the y value here, and that's how we do it, right? So next question we take up, it's I think from the second or third assignment. So what we're going to do here is Okay, so this is a question from decision trees that is used for classification and also for regression. So what it does is you're given some data and you divide, you take out rules out of it. Okay, and how do you take out rules? That depends on what the values of the different features are. And so here we use a procedure where we keep on computing the entropy. Now, simply put, what is an entropy? Entropy is basically the randomness in something. Okay, so when we are given some data, we find whether we can easily divide the data into two parts or not. So when we divide into two parts, what happens? We divide based on some feature, right? Some feature value is less than x, we put it here. Some feature value is greater than x, we put it here. So we sort of divide the data here. Okay, now, after we divide, we have some data sets here, some data points here, we have some data points here. And the final value of these data points will be mixed. More the mix, more the entropy. That is, more the randomness. Okay. So so you can imagine a sort of tree over here. We keep on dividing based on some rules, and in the end, we have the leaves that gives us the output. That give us the output. Okay. So we keep dividing based on entropy. We divide based on one feature, we compute the entropy. We divide based on the other feature, we compute the entropy, and whichever gives us the better division, that's what we go with. So here, so this is a part of that whole algorithm where we compute the information gain. So information gain we compute using the entropy. Okay, so I'm going to tell you the formula and then it will be easy for you to follow. So let's read the question first. What is the value of information gain in the following partitioning? So as I said, we keep on partitioning the given data. So we have samples, okay, and we keep on dividing them. We keep on, partitioning them. So initially, you see there are 100 data elements, and the entropy is 0.7. Okay, entropy, if you know, minus p log p, summation of minus p log p. So that's how we compute it. But here we don't have to compute that, it's given to us. Okay, 0.7 is given to us. Okay, so we are dividing the data set, we're partitioning it based on some feature. And after partitioning, in one of the subsets we have 60 elements, in the other one we have 40, and the entropy of each of the subsets is also given. So it's even more simple. We are given the entropy of both the partitions. What is required for us is to compute the information gain. Information gain basically tells us how much entropy is reduced, right? So our aim here is to reduce the entropy, because as I said, entropy means randomness, and our aim is to reduce the randomness. So once we divide, the overall entropy will go down. So how much entropy goes down is what is called the information gain. Okay, so let's see how do we do that. So this is the formula of information gain. So entropy T is the initial entropy. So I'll take it in simple terms. Information gain is equal to previous entropy minus entropy after split. Okay. So initial entropy before we partition is given to us, that is 0.7. Okay. And what is the entropy after we split? So this is the formula that we use. So basically what we do is we compute the weighted entropy, and that means in the first partition we have 60 elements, so we do 60 over 100 because 100 is the total number. Okay, so 60 over 100 multiplied by 0.4, that is the entropy of this subset, plus 40 over 100 into entropy of this subset, that is 0.2. So it comes out to be 0.32. Correct. So basically, initially we had entropy to be 0.7, and after division we have now the entropy to be 0.32. Now, how much were we able to reduce the entropy? That's the information gain. So that is equal to 0.7 minus 0.32, and that is 0.38. Okay, so that's the information gain that we get after we partition based on this feature. Okay, so in practice what we do is we will also divide or partition based on another feature, and we'll see how much information gain we get, and whichever feature gives us more gain, that's the one with which we go ahead. Okay, so again, that's a simple question. That's the answer of information gain here. Okay, so next question we take up, which is regarding KNN, that is K nearest neighbor algorithm. Okay, so again, that can be used for regression as well as classification. So if it follows a very simple idea, it's an instance based learning algorithm, and let me tell you what that means. So you can divide the algorithms, machine learning algorithms, into two types. One is model based learning and the other is instance based learning. So in model based learning, what we do is we assume some property of the data. For example, regression. Okay, for example, linear regression. We assume that the data follows some linear fashion. Okay, we assume that, and based on that only we do all the calculations, right? So that's our model. So that's a model based learning. On the other hand, we have instance based learning. Okay, so this KNN is an example of instance based learning, and what that means is we don't worry about any property of the data. We don't assume anything about the data, and sort of whatever the instances tell us, we give an answer based on that. Okay, let me give an example here. So there is a new sample for which we have to predict. Okay, we have to predict its class. We will see it's near. We will see the samples which are near to it. We will see what type they are, and based on that we will predict. Okay, so we are not assuming anything about data here. We are simply, so it's a sort of greedy algorithm. Okay, in the sense that it doesn't look at the entire data. Whenever a question is asked to it, it will look at the samples, the data items which are near to it. How many data sample it will see, that we will talk about. So that is a variable, that's a hyperparameter. Okay, so yeah, so it will look at the near neighbors, and it will see what kind they are. Based on that, it will give the answer. So here, okay, we are asked here. So here, for simplicity, in the question we have the circles, and the circles tell us, okay, there is a hyperparameter k here, k and n. K tells us how many neighbors we have to look at. Okay, if k is equal to 1, we will just see one nearest neighbor, and we'll see if it is class X, we will output class X. If it is class Y, we will output class Y. Okay, but then obviously based on one feature we may not be able to predict. That doesn't make any sense. So we need to look for more data items. So we look for example, we look for 3 data items. Okay, given this data, we look at 3 nearest neighbors, and we look at what kind they are, and based on that we give the answer. So here what we do is, in case of classification, we look at the majority. Okay, if majority of elements are X type, we output the class as X, and so on. So this K is a hyperparameter which we need to decide before we run the algorithm. Okay, so here so the circles represent k is equal to 1, 3, 7, and 9. Okay, you count the dots, and they are the number of neighbors. So green is the one. So green is the data item for whose class we have to predict. Okay, so the question is, for which values of k is the query instance classified as read by KNN? Okay, so what we are going to do is, for each value of k, we are going to check how many red and how many blues are nearest to it. Okay, so k is equal to 1. If you see the innermost circle, we have 1 blue. Okay, so the prediction is obviously blue. When k is equal to 3, what we have is we have 2 reds and 1 blue, so the prediction is going to be majority, that is red. For k is equal to 7, we have count all of them. You have to count them, the ones which are in the inner shells as well. Okay, so k is equal to 7, we have 4 blue and 3 red. The majority is blue, so we output blue. For k is equal to 9, we have 4 blue and 5 red, so majority is red. Okay, so the question was, for which values of k the instance is classified as red. So we get for k is equal to 3 and 9. Correct. So that's very simple. You just have to see what they are asking, what is given in the figure, and you have to just count them out. I think that's very simple. Okay, next question is, what is the cosine similarity between two vectors x and y? Okay, again, very simple. So we are given the two vectors. So in machine learning, there are various distance measures. Okay, there are two vectors, you have to find the distance between them. As an example, there is k-means. Okay, k-means is a clustering algorithm. So what it does is it keeps checking the distance between different vectors, and that distance is Euclidean distance. Okay, Euclidean the point to point distance. Okay, that's one sort of that's one example of a distance. Then there is Manhattan distance, and there are various other examples of distance. Now cosine similarity, or you can say cosine distance. So cosine distance is equal to 1 minus cosine similarity. So cosine similarity is another measure of finding distance between two vectors. So as the name indicates, cosine, you find the cos theta. Okay, so that's what we need to compute here. I'll share the formula with you. So if you remember from your mathematics, basic mathematics classes, A dot B, if you remember, dot product of two vectors, A dot B is equal to the magnitude of A, the magnitude of B, multiplied by cos theta. Theta is the angle between A and B. Okay. This magnitude is also called L2 norm in machine learning. So here in cosine similarity, we have to compute cos theta. So you get the value here, that is A dot B divided by L2 norm of A into L2 norm of B. Okay. So what is L2 norm? That's the magnitude. So you know the formula for that, square root of square root of sum of squares of individual elements. Okay, and A dot B is the corresponding sum of multiplication of the corresponding elements. So let's see how we do it. So A is given this, and B is given to be this, and A dot B, what will that be? So you multiply 4 by 5 plus 0 by 5 plus 0 by 4 plus 5 by 0 plus 1 by 0 plus 0 by 0 plus 0 by 0. Okay, so you get it to be 20. So that's a dot product. And then magnitude of A you get to be square root of, so individual elements, you just skip the zeros, and what you are left with is 4 square plus 5 square plus 1 square. That comes out to be this value. Similarly, you get the magnitude of B, and cos theta will come out to be this. So that is the cosine similarity between the two vectors A and B, right? So again, a very simple question. Okay, so I hope you people are writing in the chat. Let me see. Okay, good. You people are writing. Please keep writing your questions so that I can take a look at it in the end. All right. Okay. Oh, I'm sorry. Okay. Yeah, so this is done. Next question. It's on hierarchical clustering. So as I said, clustering, I talked about k-means clustering, right? That's about finding the distance between different vectors and then making clusters by finding the centroids of the clusters. So okay, let me not get into that. Let's get into what the question is asking. So hierarchical clustering. So what it does is it's a sort of bottom-up approach. So we assume every element to be in its own cluster. Okay. So if you have 100 elements, we assume them to be in their own clusters. And then what we do is we find the distance between these elements, and then based on that distance, if they are nearer to each other, we put them into same cluster. So we get different clusters. That's one level. And then again, we do the same. We whatever new clusters we have come up with, we compute the distance amongst them, and then if they are near to each other, we club them as another cluster in the next level, and so on and so forth. Okay, so it's a sort of bottom-up approach. Now, okay, so now the question is, if you can imagine this. So here we have a cluster, and here we have a cluster. So this cluster has some elements, this cluster has some elements. Now you're supposed to find the distance between these two clusters. Okay, how do we do it? Okay, can you think of it? Like what we can do is, so there are different measures that can be used. What is one is you find the the elements in the two clusters which are nearer to each other, and you find the distance between them. That's one distance measure. Okay, another is you find the elements in the two clusters which are farthest from each other. Okay, and you find the distance between them, and you use that as a distance measure. Okay, and the third one is you find the distance between all the elements and then average that out. Okay, so there are different measures that you can use. So that all comes under hierarchical clustering. Okay, so here what we are, okay, let's read the question. It's typical to work with distance measures, distance matrices between data items, and so-called proximity matrices between clusters. So here we are given 6 elements and we are given the distance between them. Now we assume 3 clusters. Okay, so assume that from A, B, C, D, E, F, you have gone up to the next level. Okay, you're going up to the next level. You have to go to A, B, C, D, and E, F. So how does the corresponding proximity matrix look like? Okay, so if you have to find distance between A, B, and C, D, so here you're assuming that A and D are a part of a cluster, C and D are a part of cluster. So you have to find the distance between A, B, and C, D. So what we do over here, okay, yeah, let's come here. So this is the matrix that is given to us. Okay, now A, B, C, D. Okay, when you only look at them, you get this part of the matrix 4, 2, 2, 4. Okay, 4, 2, 2, 4. And then what you do is you average it out. Okay, sum of 4 to 2, 4 is 12. Divide by 4, that is the number of elements, and you get 3. So that is what is the distance between A, B, and C, D. Okay, similarly, the distance between A, B, and E, F, you only look at the elements A, B, and E, F, and what you get is 5, 7, 7, 5, this part of the matrix. Again, you add them up and then divide them by 4, then you get the, okay, this one, sorry, A, B, and E, F, you get 24, divide by 4, you get the 6 average value. Similarly, C, D, and E, F, just look at C, D, and E, F, just look at that part, C, D, and E, F, 3, 5, 5, 3 in the given matrix, and you get the average distance to be 4. Okay. So this is how you compute the distance between different clusters. So what we are doing is we are averaging out the distances. All right. Another thing to keep in mind over here is that it is always going to be symmetric. Okay, which means the distance between AB and CD is going to be the same as the distance between CD and AB. Okay, so if you are in the option, of course, if you are given a matrix which is not symmetrical, that is going to be a wrong answer. So as an example, this one, okay, before I get into that, distance between AB and AB is going to be 0. I mean, right? It's a reflexive one. Okay, AB and AB is 0, CD and CD is 0. So the diagonal is always going to be 0, obviously. So this matrix you see is not symmetrical. Okay, you have on the upper triangle or on the right top you see 2, 6, 4, and the bottom left you have 3, 5, 4. So obviously this is the wrong answer. And now we have found the distance between AB and CD, that is 3, 6, 4. So this is the matrix that gets those values 3, 6, 4. So that is the correct answer. Okay, I hope that is clear. All right, so now let's come to a question on perceptron. Okay, so here again, like we discussed initially, the single artificial neuron, here we have again inputs, different inputs, and we have weights associated with these different inputs. Okay, and then we compute the weighted input, and then we, whatever we get, we apply a function over that which will be given to us. Again, that's an activation function which can be there can be different options for activation functions like sigmoid, tanh, linear, ReLU. So there can be different options for activation functions. Obviously in the question it will be given to you. So we apply that function, and what we get, that is the output, and then we compare that output with the value that that this perceptron should be predicting, whether it is correct or not. And if there is a difference, what we do is we update the weights. Okay, we keep on doing that, and finally we get the right weights, in the sense that the perceptron is able to predict what we wanted it to predict. So that's the whole workflow. Okay, so here I think it's again a very simple question. We are given, so this is the training set that is given to us. Okay, inputs are these, and this is the target. Okay, and we also have a bias. Yeah, here bias is given, which is set to 1. So bias is always added to the given input, and that's why you see over here in the table 1 is appended to each data item in the end. So that makes up the complete input to the perceptron. So 3 inputs and 1 bias. So okay, so what we are going to do is we are going to compute the weighted input as we did before, x naught into w naught plus x1 into w1 up to x3 into w3. Here x naught into w naught is actually the bias. X naught is bias, w naught is the weight of that bias. Okay. Now this is, you first have to read the question because it will tell us what sort of activation function you're supposed to use. Okay, so that outputs 1 if weighted input is greater than 0, otherwise 0. So that's the activation function over here, if you didn't note. Okay, we will use it in a while. So with initial weights are all set to 0. Okay, so you have to do some initialization. Okay, generally they do it to 0. So 0 0 0 0 is going to be the weight vector initially, as you see in this table. And then, as I said, we compare the final output with what we wanted, that is target, that is given to us again. And based on the difference between that, we update the weights. Okay, and how do we update the weights? This is again given, but you should know that as well, because sometimes it might not be given in the question. So wij plus 1, that's the new weight, and wij is the old weight. Okay, now alpha is the learning rate. So if you would have heard of it, learning rate is how fast the learning should happen, right? So that's a hyperparameter which is given to be 1 over here. Okay, so target j minus output j, as I said, we compute the difference. So target is this one, and output is what we will get from the one iteration of the perceptron. Okay, multiplied by xi, that was the input instance, this thing. Okay, 1001. So now let's get started. So what we are given is, this table is incomplete. Okay, but it's good that they have given the initial steps, so that should help you how this perceptron works, in case you still haven't understood from this very part. Okay, so let's try to follow it, and we are supposed to fill this table, and finally we have to tell the final value that comes out to over here. Okay, now, okay, we are trying to follow this this very table. Okay, now, so this is the input 1001, the first instance. So if we have n data in inputs, these inputs are fed to the perceptron one by one. Okay, so the first one that comes up is 1001, and its target should be 1. It should be 1. Okay, it hasn't come yet. It's what we are going to compare with. Then initialized, I mean, as I told you, the weight vector is initialized to 0 0 0 0. And okay, so now what we are going to do is, this instance will be multiplied by weight, because as I said in the first example, I told you, you multiply x1 w1 x, okay, it's here also, x1 w1 plus x2 w2 plus x3 w3 and so on. So you multiply 1 with 0, 0 with 0, 0 with 0, and 1 with 0, and the sum comes out to be 0. Okay, so that is our weighted input. Okay, now let's get back over here. Look at the activation function. Output 1 if weighted input is greater than 0, else 0. Now this is 0, so the output will be 0. Okay, so this is the output, and what was our target? It was 1. Okay, it's not matching, you see. So we need to change the weights, right? So how much is the difference? 1 minus 0, the difference is 1. Now let's get back to the formula for updating the weight. So since the learning rate is 1, so it is simplified to this one. You see, wij plus 1, new weight is equal to old weight plus difference of target and output multiplied by the instance. Okay, very simple. Just let's go step by step. So we get this 0 0 0 0 plus 1 multiplied by 1 0 0 1, and this is what we get. This is our new weight vector. Okay, now this new weight will be used in the next iteration when the next instance comes up. Okay, so that's what we do here. This is the next instance. This is what its target should be. This is what our updated weight is. And like we did earlier, we multiply this instance with the weight vector, and what we get is 1. Okay, now let's get back to the activation function if you don't remember. Output 1 if weighted input is greater than 0. Weighted input is greater than 0, so we get a 1 over here, and the target was 1, so difference is 0. So we are not going to make any change. So it's the same. The old weight is equal to new weight. Now this new weight will go in the next iteration with the next instance, and its target is 0. And when we multiply, when we get the weighted input, that comes out to be 2. Let's go back here. Output 1 if weighted input is less than 0, right? So it gives us 1. Okay, that's the output. Now, is it matching with the target? No. Target was 0 and we output 1. So the difference between target and output is -1. So you see, we multiply with -1. So again, we follow this formula. Old weight, that is 1001 minus 1 into xi, that comes out with this. So that's the new weight. Okay. Now in the next iteration, we use this new weight, right? Again, we get the weighted input. Now this is 0. When it was 0, you see over here, you output 0. So that's the output 0. So this target is matching with the output. So we don't make any change, and the old weight is equal to new weight. So that's what we had to find out over here. So look at the question. How will the final weight vector look like when all data items are processed? Okay. So our answer is 0, -1, 0, 0. C. Correct? So that was very, I think, interesting as well as simple if you follow all the steps. Now let's take a look at one more similar question where we have a different activation function. Okay, so it's very important that you follow use the activation function that is given. So here I'm going to show you another thing. Okay, let's first read it quickly. So we have again a single neuron, again 3 inputs and a bias set to 1. Again, we will compute the weighted input. Now that outputs activation function weighted input if weighted input is greater than 0, else 0. Now you have to clearly understand it, because I think there were a lot of questions in the forum as well regarding this. So let's try to understand this, and you have to keep in mind when you perform the calculations. So if weighted input is greater than 0, then you use this function. Okay, if weighted input is less than 0, you don't use this function. Okay, you just output 0. So, and when you use this activation function, how do you use it? So nothing else is written about it, but you have to see the figure. So in the figure, you see when the input is 2, you output 1. Okay, what does that mean? Whatever input is given to us, so it's a straight line, you see. So whatever input is given to you, you half it. If the input is 1, you make it to 0.5. If the input is 0.5, you make it 0.25. Okay, so there was a little confusion about this question. So let's quickly follow it, because there's a simple change, rest would be same. Okay, so again 1011 is the input, and target is 1, and this is the weight vector which is initialized to 0, 0, 0, 0, and weighted input will be 0. And okay, weighted input is 0. Okay, so if weighted input is 0, then output 0. Okay, so output is 0. Let's compare it with the target. It's not matching, and the difference is 1 minus 0, that is 1. So we update the weight vector that goes in the next iteration, and the weighted input comes out to be 1. So use this function corresponding to 1, you get 0.5. Okay, so that's our output. Okay, now let's compare it with target. It's not matching, so the difference is 0 minus 0.5, that is minus 0.5. Okay, so this will be our updated weight. Okay, that will go in the next iteration and so on. And again, just last instance, you get the weighted input to be 2.5. Okay, and when you put that in this activation function, what you get is 1.25. Okay, you half it. So again, when you compare, you get the difference to be minus 1.25, and so on and so forth. So the final weight vector that you get is this one. So let's look at the options. So that's the last one, second last one. Okay, so that's how you solve these questions, and I think that they're very simple if you follow them step by step. Okay, still if you have any doubt, you can write in the chat box. Okay, so another very interesting question, and very important as well. So far we've been dealing with the single neuron, single perceptron. Okay. So as I said, in artificial neural networks, we have a network of neurons where there are different layers, and these layers have different neurons. Okay. So there's not a one single neuron. So this is a practical picture. Here you see this is the input layer, this is the output layer, and we have two hidden layers. Okay. So what happens is, again, you feed the input to the input layer, and that passes through the hidden layers, and the activation functions are applied, and then it goes to the next layer and so on, and it reaches the output layer, and again we apply a function, and then we get the output. Again, we compare that output with the target that we wanted to get. If it doesn't match, okay, if it doesn't match, again we are supposed to change the weights. Okay. Now so far we just had to change the weights of one neuron, but here again we have so many weights, right? If you know the simple architecture, we have different links. So there's a link between input to one, input, second input to one, input to two, and so on. There are so many links and there are so many weights, and we are supposed to update all of them. Okay. So how we do that, that is called actually back propagation. So we get some error at the output, and then we back propagate it to all the layers, and we update the weights, and then the next data item comes, and then we get the new output, and then we compare it with what we wanted. If there is a difference, then we back propagate the error to all the layers, and the weights are updated, and so on. Okay, so that's a simple thing. So let's see what we have to do in this question. We're given the bias to be 0, learning rate is 1, activation function is identity function. Okay, which means we don't have to do anything. It's just the same. It passes on whatever it gets, it outputs. Okay, all weights are initially set to 0.1. Okay, every link has 0.1 weight, and input vector is given to be 1 2 1 comma 2, and the target is supposed to be 0.218. Okay, there is only one input here, the simplest case again. So calculate the output from neurons. That okay, when we compute the output, that's actually called the feed forward step. Okay, and when we back propagate the error, that's the back propagation step. So again, the output computation is very simple. So first question is, what is the output value y at neuron number 6? So you see 1 is the input here, x1, and 2 is x2. So 1 goes to these 3 layers. I'm sorry, 1 goes to three nodes, 3 neurons. Similarly, x2 goes to 3 neurons. Okay. So neuron number 1 gets 2 values with the weight of 0.1. So we will compute the weighted input over here at node number 1, similarly node number 2 and node number 3. Now whatever we get here, that becomes the input for node number 4 and 5. Okay, and again the weights are given, so we compute the weighted input at 4 and 5. I'm sorry, weighted output. Okay, and whatever we get over here, that becomes the input to neuron number 6, and that is what should be the answer. So let's take a look at it. You can easily do it. I'm just going through it. So output at 1 is going to be 0.1 into 1 plus 0.1 into 2, and that is 0.3. Similarly for 2 and 3. Output at 4, so what is it going to be? The output of 1 is going to be the input of 4, so we get it to be 0.09. Similarly for node number 5, the neuron number 5, so 6 will get 0.09 into 0.1 plus 0.09 into 0.1, that is 0.018. So that is the second option. Okay, yeah, very simple. Now we're going to use that answer, and then we move ahead. So what they're asking is, what is the back propagated error sensitivity at neuron number 1? Okay, yeah, right. So as I told you, we get some output at the output node, and then that we will compare with the target, and we get the difference. Okay, so that is the error at this node. Okay, and that error we are going to back propagate to all the nodes. So it goes step by step. Whatever error we get here, that is back propagated to 4 and 5. And then we do some computation, then that error is propagated to 1, 2, and 3. Okay. So, okay, if you want to look at the big picture, it's like, see, we got some error here. Okay. Now, how much of this error this node would have contributed to? That's a simple thing here. So based on that, so we get the error sensitivity of every node, every neuron, and based on that we update its weight. Okay, so that's the next step. We will go there. So for now, what is a back propagated error sensitivity at neuron number 1? We right now have the difference of the output and the target. Over here we have to back propagate it to the previous level, and then that will be back propagated to the previous level at node number 1, which we have to compute. Okay. All right. So this is what is given. So error sensitivity, or you can say error at node number 6, is 0.218 minus 0.018. This is what we got here, and this is what was target. So we get 0.2. Now this error 0.2, how much of this error came from this node, and how much of that, because whatever this gets from this node. Okay, so there is a dependency. So we will go first to node 4 and then to 1. So okay, this is the formula that we use. Back propagate error sensitivity at internal nodes I is equal to, that is di, is equal to sum of wij. Okay, if you have to compute at a given node, what you do is wij to dj. Dj is the difference, that is 0.2. Okay, that is actually the sensitivity at the next node. So basically the error sensitivity at node 4 will be 0.1 into 0.2. Okay. Similarly, the error sensitivity at node 5 will be 0.1, that is the weight, into 0.2, that is 0.02. Now we have reached here. Okay, and then we have to go one step back. No, the error sensitivity at node number 1 will be, we will look at all the outgoing nodes, outgoing links, which are 2 over here. Okay, so weight of that into the error sensitivity of this node, that comes out to be 0.1 into 0.02 plus 0.1 into 0.02, and that comes out to be 0.004. Okay, that's what was the question. What is the back propagated error sensitivity at node number 1? Right, that is 0.004. Similarly, for 2 also it will be the same. For 3 also it will be the same, because they are having a similar structure. Okay. Next question. This is also it's a question which is based on this very answer. Third question, that is, what is the updated weight for connection between input x1 and neuron number 1? That is this one. Okay. So as I said, our aim is to update the weights based on how much error we get here. So so before we update the weights, we need to compute what is the error sensitivity at each node, correct? Which we computed over here. So error sensitivity at node number 1 is 0.004. This node. Okay. And what we have to do is we have to update this weight based on that error sensitivity. So updating weight, this is the formula. So this is the new weight and this is the old weight. Wij is equal to Wij plus learning rate, which is 1 here, into dj. Dj is the error sensitivity of this node multiplied by the input, which is 1. Okay. So updated weight for connection between x1 and node 1 is equal to 0.1, which is the old weight, plus 1 into 0.004, that is dj, into 1. So that comes out to be 0.104. Okay. So earlier the weight was, in the previous iteration, the weight was 0.1, and now after 1 pass, the weight is updated to 0.104. So there's a small change. So that is how we do it, and we do it for all the links. And then we again compute the next, the output of the next instance, and then we compare, and then we back propagate, and so on. Okay. I'll quickly take a look at the questions. Oh, okay. Okay, it's good that you people are typing. I'll get back to it very quickly. So let me cover a few more questions, and then I'll get back to the question that you're having. So, okay, this is a very simple question, I think. So a network is given to you, and And it is given to us that the dynamic programming approach for computing shortest distance gives us 14. What would a greedy forward search give? I think it's very, very simple. You would have done it in data structures, right? So in greedy approach, what we do is at each step we take a greedy decision. Okay, so we have to find the distance between S and T. So we are at node S and we don't know. So what we know, we only make a greedy decision over here at this node. We don't know what are the distances later on. We are not concerned about them. At being at node number S, we only look at three links. Okay, and the distances between them are 5, 4, and 6. And the minimum distance from S is towards B, which is 4. Okay, so we make that choice. Okay, we are not concerned what comes up later. It may happen that later on we end up following a path which is taking more, which is having more cost, but we don't care about that. As in it's a greedy approach. So that is why greedy doesn't always give us optimal solution. Dynamic programming gives us an optimal solution because it checks what is going to come ahead. Okay, it goes step by step. So anyway, so here we have to find the greedy solution. So at S we choose B at a distance of 4. Now we are at B, and the distances that we are going, which are coming out of it, are 12, 13, and 18, and the minimum is 12, right, to D. So we follow that path, and again there is only one path. We follow that. So the cost, okay, yeah, this one. So the cost will come out to be 4 plus 10 plus 10, that is 26. Very simple question again. Okay, so this is a question from reinforcement learning. So if you know the basics, if you know robots, how we make them, move from one place to the other, that is a part of reinforcement learning. So what we do is, if the robot takes move from one place to the other, we have rewards associated with each step, with each state. Okay, so there are different states, and you imagine a robot going from one state to the other. Now we cannot control it, right? It has to learn from there. It has to learn. If it gets a reward, that means it's a good move. If it gets a negative reward, that means it is not supposed to take that move. So that sort of thing. So what we are given are the rewards for moving from one state to the other. So this is the scenario here. This is a space where this robot, this blue dot, has to move, and we are given the rewards. So these are the terminal states, the red ones, and this green one is the target where it should reach. And the reward that we get for reaching here is 4, and the reward for yellow ones is 1, and for red ones is -4, because we are getting a penalty for reaching a wrong state. Okay. So what we have to do over here, so this is a question from Q learning. Okay. In Q learning, we are given the Q values, and we have to update them based on how it moves from one state to the other. So there are two, you can say, episodes of moving. One is it goes from 12 to 13 to 14 to 15, okay, in the east direction. And the other one is 12 to 7, and then it moves from 7 to 8 to 9 to 10, and we have the rewards, and this table tells us the Q values. Okay, what we have to do over here is to update the Q values, right? And I think in the question, okay, this is a question, yeah, right? So in the question, after following these two episodes, we have to tell us the updated Q values. Okay, these are the initial values, and this is a formula which is also given, although you should keep that in mind, but it is given in the question. So yeah, so this is the formula. When alpha and gamma are equal to 1, they are again hyperparameters here. So QSA, this is the updated Q value. R is the reward for moving from state S by taking an action at state S. And Q, this is the max value. All right, so I'll take an example over here, which will make it clear. So what we have to do is, after following these two episodes, the updated values. So if it moves from 12 east, how much it should be, how much Q value, after moving from 13 to east, how much Q value, 14 east, how much Q value, and so on. This is what we have to tell. So we follow this formula. So the value of Q for 12E, okay, 12E will be 1 plus 0. How do we get that? You see, if you are at 12 and you go in the east direction, okay, what do we get? The reward is 1, right? The reward is 1. This is given over here. So 1 plus maximum of Q S dash A dash. When you move at east, whichever action you can take from there, you take a max of that. Okay. So over here from 12, you move to 13 and all the Q values are 0 and the maximum of that will be 0. So ultimately you update it to 1 plus 0, that is 1. Okay. Let's take another example over here. When you move from 14 to east, okay, this is 14 and you're moving towards east. Okay. This is 14. When you're moving towards east, you get a negative reward. That is -4, right? You're moving from this state to the red state. So you get a -4 reward. So you write -4 here. Now, when you reach 15, okay, from 15, whichever action you take, these are the Q values. From 15, if you go north, south, west, east, these are the Q values. You take the maximum out of these, which is -2, and you sum it up, you get -6. So this is the updated Q value. Okay. Just last one we will take and then we will switch to the question. So Q for 9E, right? So 9 is this state and you're moving to the final state. So you get a reward of 4, right? So reward is 4. And now when you move to state 10, from 10 you see wherever you move you get 2, 2, 2. Okay. The maximum is 2. So you get total of 4 plus 2 is equal to 6. Right? So that's how you compute all the values. So that's how you'll be answering this question. Okay, so let me now take a few questions. Okay, you people are asking particular questions from the assignment. So I can see question 11 from assignment 4, which was related to KNN. I've just discussed this question. I think, I don't know, you could have missed it. This KNN question I just discussed. Okay. Okay, by taking half of it in the activation function. So activation function will be given to you. And okay, I'll go back to that slide. So this activation function you're talking about. So this will be given to you. Okay, we use different activation functions for different scenarios. So I will not get into the details of which scenario you use which activation function, because that I think is not discussed with you. So for now, you just keep in mind that the function will be given to you. In this case, the function is given in the form of an image. Okay. So in the image, you see 2 and 1. When 2 is there, when input is 2, then output is 1, and so on. So you can understand that when the input is 1, you half it. So that's why we are using this activation function. Okay. You may please write more questions. Okay. Okay, I don't see more questions. Okay. So you people are referring to a few number questions. It will be nice if you write the topic name so that I can discuss that. Week 6 assignment question 9. If you could refer to that, it will be helpful. Anyway, so whichever questions are left, we can take that up in the forum. So there's no problem as such. I think I have covered many of the questions from the assignment, so I don't think it will be difficult for you to cover them now. I think you'll be able to solve them. Okay, I'll take up a couple of more questions and then we will call it a day. And before we leave, you can ask more questions in the forum as well as in the chat, so there's no problem as such. All right, we'll just quickly take this question. Again, this is from decision trees. So very simple question. We are given this table, okay, and these are the features, and these are the final targets. And as I said, in decision tree, it divides and provides us some rules as an output. The output of the algorithm are different rules based on which we divide. So given a new instance, you just follow the path, and whatever you get as the leaf is the output. So here the question is, how are the 14 data items in the provided data set distributed on the leaves of the decision tree above? Okay, so what we're going to do is, in this question, take a couple of minutes when some sort of question is asked to you in exam. What you have to do is you have to take each data sample and follow the tree and note down the leaf. Okay, for example, first feature on which we are dividing is outlook. Okay, so outlook of the first one is rainy. We go over here, rainy, and now it is asking us what is the humidity. So humidity is high, so we go over here and we reach at this leaf, which means D. Okay, so we make a note over here. So like this we will make a note of all the instances. So we get D over here. Let's follow one more. So rainy, we reach here, outlook is rainy, and then humidity again is high, and right, humidity is high, again we come to D. Okay, so we note down D. Let's check one more. So when outlook is overcast, we reach over here, and after overcast there is no other branch, which means we are ultimately at leaf C. So we notice C over here. Okay, and so on. So you're going to note down the sequence for all the data items, and then you count how many are reaching A, how many are reaching B, and so on. Right. So yeah, that's all. You can note over here that this temp feature is not being used in the tree. Okay, so that may happen. So in practice, we might not use all the features because that leads to overfitting, because right, that will be very specific to that data set, which we don't desire. So we leave out a few features based on whether, again, whether they tend to reduce the entropy or not. So that's how we go about it. Yeah, so I think it's pretty much it. Right, so we'll call it off. You can still ask more questions over the forum. So yeah, okay, all the best to you. Do well. One of the questions on the forum was, how do I pass the exam? So you just follow all the videos and you try to solve all the assignments. And I think now you'll be able to solve the assignments. You won't face any problem because I've covered most of them. So yeah, I don't think there'll be any problem if you follow all the videos and the assignments, right? Okay, good luck. Sir, you can stop it now.
Yeah, okay, thank you.
Yeah, thank you.